Okay, welcome to a Thursday afternoon in music and physics. And now that you've taken quiz two and turned that in, want to go over it. And again, this one didn't happen to need the calculator, but I guarantee you the quiz three next Tuesday, you will definitely want to have a calculator, and we cannot let you use cell phone calculators. So please get yourself a cheap calculator and just throw it in your backpack and bring it every day. So this basically is just asking a few questions about the NOVA video that we had you watch. And so the revolutionary breakthrough described in the video that allows us to make violins that sound like antique Stradivarius violins came from the observation that the wood was aged in water, and therefore what? And we don't want a novel, we just want the basic element there. But the key difference is that because it was aged in water, the bacteria ate away these cell membranes. And so instead of having a bunch of air bubbles inside the wood, it was like a sort of just a set of just empty kind of just the ribs. And in fact, you remember when he put the two samples of wood in water, the one that was aged in water because the cell membranes were there and didn't trap the air, that sank in the water, and the other piece of wood floated. And so you can imagine if you don't have the cell membranes, that's impeding the movement of air, which that's what generates the sound waves, it's vibrations in air, and that makes a big difference. And apparently that's a key element. And so Najaveri was able to get quality violins very, very similar to Stradivarius. And that seems to be a key difference. He thinks the varnish was also important, but it seems like the one we were looking for was basically that the cell membranes were gone, and so basically that's the key. So what was the point of the demonstration? The orchestra playing Tchaikovsky's number six symphony, and why do they stand up and move? And what this was demonstrating, Tchaikovsky was using a rather clever approach. The melody you heard was not played by any single instrument. Basically, the melody was traded note by note between the first and second violins. And so basically, because you're used to hearing, when you hear a lyrical passage, the notes are typically close to each other in pitch. They don't jump around much, even though the first violin was going bebop, 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 and the second violin was going bop, beep, bop, beep, bop, beep. What you heard was two phrases, a top line and a bottom line, but no instrument was actually playing that. And so that's what they were trying to demonstrate. And it's a neat trick. And that, as we said, that gets into the psychoacoustics of how your brain processes instruments. And also Dana Doge demonstrated that with the headphones in the video. So again, we did want a novel. If you got that basic idea, that's what we were looking for. Finally, they showed you the new bells. And the new bells had that funny shape. It didn't have the characteristic bell shape. The top had sort of a bulge. And because of that, the overtones, or well, bells don't have overtones, but the harmonics of the bell, the typical bell shape has a resonance a third above the fundamental and a minor third above the fundamental. And these new bells had shifted the resonance to be a major third above the fundamental. And so that's how one example of how the shape affects the resonances. And then what was interesting when they played the carillon with the new bells, they played it for a set of experienced carillon players, and then they played it for musicians, but they weren't carillon players. And the carillon players preferred the old set with a minor third, but the people that weren't carillon players seem to prefer the new bells with the major third. It gives a little bit brighter tone, less dissonance. And so again, that's sort of a psychological effect. The carillon players are used to the minor third, so that's what they want to hear. They like the old bells, but these new bells, for someone that hasn't been exposed to it before, they seem to like the major third. So yeah, and let me go ahead and invite Professor Baker to pause here if you'd like to discuss some more of the. I mean, there were very many demonstrations, and if you like to discuss some, or some of the students have some they like to bring up or found interesting, I invite you to do that. And while you go ahead and maybe pause the video, I'm going to switch over to, here we go. Um, I'm going to switch over to, this is from the handout and the set of notes that I gave, the set of notes I gave on the units. So this is what you will need for quiz number 3 on Tuesday. So take a look at this. We'll give you the formulas, but you need to know how to use them. So these are some of the basic math skills that we need. So for example, in this case, here's the formula that I'll give you that'll be in your formula sheet. Distance is velocity times time. And so if your velocity is 50 miles per hour and your time is 4 hours, for example, that's driving from Dallas to Austin, let's work that out. It's not just 50 times 4, which is 200, but let's check the units, because the units are sort of a sanity check to make sure we're doing it correctly. And if I multiply miles per hour, I have hours downstairs and hours upstairs, those cancel, and I'm left with units of miles alone, and 50 times 4 is 200. So I operate on the units as much as I operate on the numbers. Okay, and this is a very powerful way of checking. It'll allow me to see if I made a mistake or not. For example, let's make a slight modification of this. If I ask you not for the distance, but let's suppose I ask you for the time. Say I want to travel 200 miles to Austin and I'm going to drive 50 miles an hour. How long does it take me? And again, I've picked an example so simple you can probably just do this in your head intuitively. But what I can do is I take this formula and I divide both sides by V. So I divide this by V, and I divide this by V, and that'll cancel out. And so time is X over V. And so this is a manipulation I have here. And just to make sure I've got that right, let's carry the units through and make sure. So I claim time is equal to distance over velocity. So if I have 200 miles and I'm going 50 miles per hour, the miles upstairs cancels the miles downstairs. But what about this hour? I have 1 over 1 over hour. And so I reciprocate, but I reciprocate again. 1 over 1 over is just the same as hours. Okay, so if I turn it upside down once and turn it upside down again, I get back. So the units is hours, the time is 4, and it takes 4 hours to drive to Austin. And sure enough, that cross checks with the example we had up above. Okay, so these, it's very basic, but these are the kind of things we want to make sure you can do. Now, occasionally we'll need you to convert units, because we're typically work in meters per second, but sometimes we'll want to work in different units. For example, the speed of sound is about 350 meters per second, but you may not intuitively know what meters per second is. You're more familiar with miles per hour. So we'll need to convert a little bit. And so let me show you how to do conversions. And I always like to warm up on one where I know the answer. Okay, so let's pick something really simple, and then we'll use this to sort of test to make sure we have the mathematical approach right. So 1 yard is equal 3 feet. Okay, hopefully that's a common knowledge. So 1 yard, a yardstick is just 3 feet. All right, 36 inches. So if I divide both sides by 1 yard, okay, 3 feet over 1 yard, okay, that equals 1. So here's a fancy way of writing 1. 3 feet is the same as 1 yard. It's like saying if I take 37 divided by 37, that's 1. It's the same thing. But I'm writing 1 in this special form. Okay, and what can I do with that? Well, if I have 100 yards, okay, if I have 100 yards, I'm going to multiply that by 1. And if I multiply it by 1, I won't have changed it, but I multiply it in this funny form. I multiply it by this, where I have 3 feet over 1 yard. And now let's look at the units. I have yards on top, I have yards on the bottom, so I can cancel out the yards, and then my units is left with feet. And so my units is just plain feet. And then I multiply the numbers. 100 times 3 is 300, and that's 300 feet. Okay. And that, you probably know, 100 yards is the length of a football field. And if you say how many feet is that, it's about 300 feet. Okay. So this is how we're going to do conversions. We're going to take something and we're going to multiply it by 1, but we're going to multiply it by 1 in a special form, and that allows me to do it. And when you do conversions, you let the units guide you, okay? Because here I want to get rid of yards, so I have yards upstairs. If I put yards downstairs, that will cancel, and that leaves me with feet. So let me do a slightly more complicated one. And I invite you to take a close look at this, because I'm actually going to ask you something like this on the quiz on Thursday. So as I said, the speed of sound is about 350 meters per second. Okay. But that's great, but we don't have an intuitive feel of that. Okay. If I'm driving my car down the highway, how many meters per second I'm going, I don't know. My speedometer reads miles per hour. So I want to convert meters per second into miles per hour. Okay. And then I'm going to do that. I'm going to do that by multiplying this quantity by 1 a whole bunch of times. And if I multiply it by 1, I'll still have the same value. It'll just have different units. Okay. And then what I do is, if you would pretend for a moment, ignore the red. Okay. Pretend the red is not there at all. I let the units guide me. Somehow I need to convert seconds into hours. Well, I don't know how many seconds in an hour, but I do know how many seconds. I do know how many seconds are in a minute, and I know how many minutes are in an hour. And so look what this does. The seconds cancel up and down, the minutes cancel up and down, and that allows me to get hours. So I let the units guide me. Okay, I have seconds downstairs. This will cancel, and I'm left with hours. Now, what about the meters? Well, I don't remember how many meters are in a mile, but I do know that I do know how many meters are in a kilometer. Okay, so meters cancels here, and that gets me to kilometers. And then I do know that how many kilometers are in a mile. So this meter cancels with this meter, this kilometer cancels with this, and I'm left with miles. Okay. And so even before I put the numbers in, what I do is I put in the units, and that tells me this cancels, hours downstairs, this cancels, miles upstairs, and that gives me miles per hour. So once I've done the units, that's the hard work. I just fill in the number. Okay. And I'm multiplying this by 1. And I happen to know that 1 minute, okay, 1 minute is 60 seconds. 1 hour is 60 minutes. 1,000 meters is 1 kilometer, and 1 mile is about 1.6 kilometers. Okay. And if you multiply all that out, you get 780. Okay. Now, this conversion, again, take a look at this. The video, I'll have it on YouTube. This will also be on Canvas under Panopto. So take a look, because this is as complicated as it gets. But these are the kind of things we're going to do, and I'll step you through this step at a time. But we do want to go through this. But this is something, because we're talking a lot about the speed of sound. It's nice to have an approximate idea of what this is. So basically, the speed of sound is about 700-ish miles per hour. Now, there's a nice approximate relationship because if you notice, if you take 350 and double it, 350 doubled is 700. And so basically, if you take the number in meters per second and double it, that gives you miles per hour. Okay. And so 350 doubled is 700. It's off by about 10%. It's low by 10%, but that's close enough. Okay. And then you can go back the other way. If you say 700 miles an hour-ish is about 350 meters per second. And so now if I ask you, if I tell you I'm driving down the highway at 60 miles per hour, how many of that, what is that in meters per second? Well, you know it's a factor of two. I just take 60 miles per hour, I divide by two, and it's about 30 meters per second. Okay, we're off by 10%. It's actually more like 26, but that gives you the ballpark. Okay, and so when we're talking about these things, that gives you an idea. Okay, so 700 miles an hour, 780 in this case, that's about a little bit faster than a plane flies. Most planes fly if you do long distance, you're probably going about 650 miles an hour. They stay under the speed of sound. The SST Concorde would go above the speed of sound. That's more complicated, but planes these days go probably 600 or so. They stay below the speed of sound. So that's the speed, that's the ballpark speed of sound. And then 60, 70 miles an hour, you're at a tenth the speed of sound. So that gives you an idea. That also means, for example, let me see if I put this in notes. Um, yeah, that also means, suppose I wanted to make a phone call. Suppose I wanted to make a phone call, 700 miles away. Um, so if I use a sound tube, to direct my voice down a sound tube, if the sound tube is 780 miles long, it would take an hour for my sound to get to the other end of the sound tube. Okay. So if I tried to make a telephone system by stringing sound tubes across the country from New York to San Francisco, that wouldn't work very well because that's about 2,800, 3,000 miles, and it would take me about 4 hours. If I say hello, 4 hours later, my voice vibrations would get to San Francisco and they could say, yes, what do you want? And then 8 hours round trip, I get the answer. So it's a good thing we convert the sound vibrations into electrical vibrations, and those travel at the speed of light instead of the speed of sound. So anyway, that's the conversion. That's as complicated as it gets. We'll step you through something like this, but things like this you will need to be able to do, and you'll do that in the lab. Let me do one other example that you're going to need to know for the exam or quiz on Tuesday. This is one of the key formulas we're going to be using throughout. It says the velocity of the wave is equal to the frequency times the wavelength. Okay, velocity, frequency, wavelength. Okay, so let's take A440. Let's take your tuning note. Okay, and then uh, that's measured in hertz, and hertz is cycles per second. Okay, and cycles doesn't have a unit. Our three fundamental units are length, time, and mass. So cycles per second. Second is a unit, but cycles is just that doesn't have a unit. I'm just going to write that as 1/seconds. Okay, and then velocity is 350 meters per second. So if I take this formula and divide both sides by f, okay, that means lambda is, I put the f downstairs, lambda, the wavelength, is the velocity over the frequency. And so if my velocity is 350 meters per second, my frequency is 440 hertz or 440 cycles per second. You see I have 1/seconds, 1/seconds. Those will cancel. I'm left with meters, and this comes about to be about 0.8 meters or 80 centimeters. Okay, So that's a little bit over 2 feet. Okay, so that's your A440 wavelength. It's about 2 feet. Okay, um, so that's useful. Now, for a 16-foot organ pipe, we want to figure out the frequency of that. And we'll get into this later. It turns out if it's a stopped organ pipe, if it's a 16-foot organ pipe, that fits half a wavelength. And so if 16 feet is a half wavelength, a full wavelength is 32 feet. Okay. And 32 feet, remember, 3 yard, a yard is 3 feet, and a yard is about the same as a meter. So, that's going to be about 10 meters, exact, more precisely 9.6. So if the wavelength is 9.6 meters and the velocity of sound is 350 meters per second, um, from the above formula, we get the frequency is velocity over lambda. And I'm just going to do the units to make sure I haven't messed up the formula. If I had written this upside down or something like that, the units would tell me. And so I put velocity up here, 350 meters per second. And downstairs, I put the wavelength in meters. I have meters upstairs, meters downstairs. The meters cancels, and I'm left with 1/seconds or cycles per second. That's hertz. Okay. And basically, 350 divided by approximately 10, it's about 35 or 36. I get about 36 hertz. Okay. So a 16-foot stopped organ pipe with a 32-foot wavelength has a hertz frequency of about 36 hertz. And your range of hearing goes from about 20 hertz to 20,000 hertz. So that's way down in the bass. That's pushing near the bottom of where you can hear. And again, Professor Baker can tell you about that, and we'll give you a demonstration on the organ. Okay. And then, yeah, down here, 1 foot is about 0.3 meters. Okay. A foot is a third of a yard, and a little bit less is about 0.3 meters. Okay. So here's the actual conversion. Um, if I, if I have 32 feet, I want to convert that. I have feet downstairs and meters upstairs. The feet cancel. I'm left with meters. I have 32 times 0.03. That's 0.96. Okay. So those are the kind of things. Those are the kind of things we expect you to do. This one, I mean, this is a little complicated. We won't have you do this on your own. We'll guide you for something like this. But something down here, these kind of calculations are things we'll be doing all the time because we'll be talking about the length of organ pipes, the length of brass instruments, the length of woodwinds, things like that. So these are the basic things that you need to be able to do. So feel free and pause here. And if you have any questions, either Brandon or Professor Baker can fill you in. But do take a look at these because these types of calculations are things that we'll have you do for the quiz on Tuesday. And remember, 2 out of 3 is full credit. So if you get 2 out of 3, you're good on that. The last thing I want to do is I will change gears a little bit. And since we're talking about lengths, we'd be remiss if we sent you out of here and didn't give you a general idea of the length of things in the universe. And so along those lines, we're going to show you a 9-minute video called Powers of 10. This was created a long time ago, back in 1977, but it's very creative. I think it's very creative. It's a very creative video, and so it gives you an idea of the scale of the universe, and both the large scale and the small scale. And so before I show the video, I just want to review some of the scales that you see. And so, for example, if I ask you, how far is it to the moon? I don't know that, it's so many miles, a big number of miles, and I can't remember, is it a million, 1,000, a billion, whatever. But for large scales, miles, really, that's not a convenient measure. But something that's more useful, and at least for me, that's easy to remember, is it takes light about 1 second to go from the Earth to the moon. Okay, the distance is just somewhere over 200,000 miles, and the speed of light is 186,000 miles per second. So actually, it's a little bit over 1 second, but ballpark. So that means when the astronauts, well, they weren't on the moon when they did it, but if the astronauts were on the moon and said, Houston, we have a problem, it would take 1 second for that information to be communicated to Houston. Okay. So we call that distance a light second. It takes light 1 second to go from here to the moon. Okay. What about how far is the sun? Again, that's a big number of miles. And, I don't remember, is it 10 to the ninth, the 10th, the 11th? I don't remember. But a useful measure is it takes 8 minutes for light to get from the sun to the earth. So let's suppose that, some alien force came along and they turned the sun off. And all of a sudden the sun stopped shining instantly. You would not know that for 8 minutes because it would take 8 minutes for the darkness or the lack of uh, photons to go from the sun to you. Okay, or when there's a solar flare in the it spouts out a bunch of particles that emit bursts of light. It will take 8 minutes for that light to get from you to the Earth. The protons it throws out take about 2-3 days, a little longer, but the light takes 8 minutes. How about Pluto? Okay, if we send a Explorer probe out to Pluto and we say take a picture, it will take 5.5 hours for that message to get out to Pluto. Okay, and then if we say send the picture back, it'll take 5.5 hours for that to get back. What about to the nearest star? Alpha Centauri is the nearest star, and it takes light 4 years to get there. Okay, so traveling at the speed of light, it would take you 4 years to get there. And of course, astronauts can't travel that fast. So if you wanted to go visit the nearest star, it would take you at least 4 years, and something less than that, depending on how fast you go. How about the Milky Way? Our Milky Way, it would take about 100,000 years for light to cross the Milky Way. Okay, that's the size of our Milky Way. And what about to see at the edge of the visible universe? Well, that's 13 billion years. And we don't know how big our universe is because our universe is only 13 billion years old. And so we can only see things that are farther than 13 billion light years from us. They haven't had time for the light to get to us. So we can only see out to 13 billion years. So as you go through this video, you might make a reference of these distances, and they're sort of useful. And we'll come back to this after the video. It also goes down to the small scale, and there are lots of distances. But the one I like you to remember in this case, I'd like you to remember three numbers: 10 to the minus 5, 10 to the minus 10, and 10 to the minus 15. And those are the scales of biology, chemistry, and physics. Okay, and when you're down at 10 to the minus 5 meters, that's the scale of DNA. So you'll see that's the scale of DNA inside the cells in biology. Okay. What about 10 to the minus 10th meters? That's the scale of chemistry. That's the scale of the chemical bonds. And in fact, 10 to the minus 10th meter, we actually have a name for that. That's called an angstrom. Okay. And that angstrom, that's a typical bond length of various molecules. For example, salt, sodium chloride, I think that's about a half an angstrom, something of that order. So the typical bond length for chemistry is on that scale, and chemistry is dealing with the bonding of the atoms. And then for physics, that gets down to the proton level. And 10 to the minus 15 meters, we actually have a unit for that. It's not as common, but there is a unit. It's called a Fermi. And that's the size of a proton. Okay. And then if you put a bunch of protons together to build a nucleus, like a lead nucleus, that's something like 10 to the minus 14 meters or about 10 Fermi. Okay. And then we've probed inside the proton and we've discovered there are quarks inside the proton at smaller scales, somewhere around 10 to the minus 18th. We've also tried to probe inside the electron, but to the extent we've been able to, as far as we can tell, the electron is a point-like object. So we've probed the electron down to 10 to the minus 18, 10 to the minus 19 meters, As far as we can tell, the electron is not made up of anything. It's a point-like object. But anyway, those are some references as you go. So if you would, I would to play the video. And if you go to the class webpage, if you go to the class Google Doc, and then from there, if you go to the notes page, at the top here, you will see I have a link here. Come on. Uh, and and that will open the Powers of 10 video. And if you would play that, if you'd play that, and then let me pause that. If you'd play that and then come back, and then I'd ask, you know, just Brandon, Professor Baker, just to kind of put this back up again, and see if you can reference these. These sort of scales are useful to give you an idea of how large the universe is, and then how small it is. And going from the smallest scale at 10 to the minus 15th meters to the largest scale at about 13 billion light years, that's about 40 orders of magnitude. So it's a remarkable in that dynamic range. And one of the interesting things about physics are the laws of physics apply across that full dynamic range. It's not like the laws of physics only apply down here, and then you have to change another set of laws and another set of laws. The laws of physics, gravity, electromagnetism, the strong interaction apply all the way from the smallest scales we've discovered to the largest scales of the universe. And that's something quite elegant about physics. So I will stop here. I will let Brandon play the video and then just come back to this slide if you would. Let me just make this a little bit smaller, and then you can comment about that, but I'll leave it here. So thank you for your attention. And again, I apologize I can't be there in person, but I will be there in person on Tuesday. And I hope you have a good weekend. Thank you much. So Brandon, over to you.